This mirror represents, it's a convex mirror. The convex mirror is the one where it's like looking at the outside of a spoon, this side. Okay. You see these in some like hallways. It allows you to it helps you to see around the corner better. Circle K might have it to be able to see around the aisles. Your passenger side view mirror is a convex mirror. It only results in one type of image, and that is a virtual image that is smaller and upright, always, no matter what. Your focal, remember this thing's actually curved like this, and here's the shiny side over here. Again, it's curved like this. Imagine a big sphere. This is the focal point, not the center, but the focal point is right there. And in this problem, I made the focal length -3 meters, and I've used 10 centimeters to represent every meter. So there's your focal point, -3, because it's behind the mirror. The object is 7 meters in front of the mirror. So there's DO. And then HO, that's the height of the object, is 9 centimeters. We're going to look for the usual suspects. DI, where's the image located? What's the magnification? What's the size of the image? Okay. We always draw the same initial ray. Whoopsies. We always draw the same initial ray, which is the one that goes parallel to the principal axis. Parallel to the principal axis. So this is a light ray that's traveling from the top of the object, traveling parallel to the principal axis, strikes the mirror. And remember, the definition of the focal point is any light ray. I just drew this one, but any light ray that is parallel to the principal axis reflects, in this case, away, right? They diverge. But if you draw them backwards, they all converge at a point. All incident parallel light rays reflect away from each other, but if you draw them all backwards, they come to a point right here. That's the definition of the focal point. That's why we choose this first ray, because that's where we know where it goes. We know that it travels that direction, where it reflects. I'm going to draw this backwards with a dashed line because this is not real back here. Remember, this is behind the mirror. This is real. The light reflects that way. Oops. So the next one, this is kind of an odd one. But we line up the top of the object and the focal point. Remember, that's the second ray where we draw from the top of the object to the focal point, and it reflects back parallel. Again, but it never gets there because it strikes the mirror. And when it strikes the mirror, that didn't quite make it. When it strikes the mirror, it's going to reflect back parallel. It reflects that way. Remember that in the previous concave mirrors, we drew a light ray through from the top of the object through the focal point, reflecting back parallel to the principal axis. So we did the same thing here. Top of the object, the red ray, top of the object to the focal point, but it never gets there because it strikes the mirror and it reflects back parallel to the principal axis. It's the reflected rays that you draw backwards. Remember, we're talking about images formed by reflection. When you remember that, it makes sense, because I'll get the question every once in a while, which ray do I draw backwards? Which ones are the ones I'm looking for in terms of intersections? Reflection, because we're talking about reflected images. So the ones that are coming away from the mirror, wherever they meet, that's where the image is. So that one this has hit the mirror and reflected that way. This incident red ray hits the mirror and reflected back that way. Those are the two I do backwards. And where they meet is the top of the object. It represents that point right here, whatever that is for this object. That's its image right there. So to represent the whole thing, because this is the whole object, the whole arrow, not just the top, but the whole arrow. To represent the whole object, you draw an upright arrow. And it's upright because you go from the principal axis up. If those points were down here somewhere, you draw from the principal axis down, it would be an upside down image, but you'd never get that in this type of scenario. This is a virtual image. Because it's behind the mirror. The reflected rays are really over here on the shiny side. It's smaller, it's upright. We could measure this, again I drew it to scale. That's about negative 21-ish, roughly. That's approximately negative 21 centimeters. I'm sorry, meters, so 2.1 meters, because I drew it to scale like that. So negative 2.1 meters, the way that my scale, again, was 10 centimeters for every meter. In terms of the height, I left it in centimeters, and that's about roughly 2.5. The height of the image is roughly 2.5 centimeters. I left my heights in centimeters. I drew this 9 centimeters tall, that arrow, and now this one's only about 2.5. Now let's go ahead and calculate mathematically what the actual values are. So to find the image, remember that use the mirror equation, 1 over f equals 1 over do plus 1 over di. So we're solving for 1 over di. That would equal 1 over, subtract 1 over do to the other side, and flip them around. 1 over f is 1 over negative 3. Don't forget the negative sign. Minus, because I subtracted that to the other side, minus 1 over 7. And that, I've already done the math, comes out to negative 0.48. Negative 0.48. That's not the answer, right? Because I'm looking for di, not 1 over di. So take the reciprocal of that, and di equals negative 2.1. Hey, what do you know? Negative 2.1 meters. That was just for my drawing, and that's mathematically. I don't normally get it exactly on. How cool is that? Okay, the magnification. Magnification equation is negative di over do. And so that negative sign is part of the equation. That negative sign is part of the value of di, so you have two negatives here. That negative sign and then this negative sign is going to give you a positive value, which makes sense because it doesn't turn over. Divided by do, which we said was 7. And so that equals 0.3, positive 0.3 times. What does that mean? It means that it's 0.3 the original, the image is 0.3 times the original height. That's 30%. So it's only 30% the original height of the object. And then you can find the height of the image using m equals hi over ho. So 0.3 equals hi all over, what did I say, 9 centimeters is the height of the object. And so multiply 9 to the other side. 0.3 times 9, I think, is 2.7. So hi equals, let me just double, 2.7 centimeters. That's the height of the image. All right? Notice that the image is always going to be closer because of the way of the configuration. It will always be closer to the mirror than the focal point. The image, it's always smaller than the object, than the actual object. And the image is always closer to the mirror than the object is closer. So in a car, when it says objects, that message on the side view mirror that says objects are closer than they appear, it's really not true. The image is closer than the object, but it's also smaller. And so I think our brain thinks it's further away because it's smaller. But anyhow, a convex mirror will always make a virtual image. That's going to be negative because it's behind here. Numerically, because that's negative, it's virtual. From the ray diagram, you know it's virtual because it's behind the mirror. It's always going to be a magnification that's positive and less than 1, always. So that means it's smaller, and it does not turn upside down. It does not invert. It stays upright. Okay, so it's positive, upright, virtual.